So thank you for presenting your joint work on a connectomic hypothesis for the hominization of the brain. We look forward to it.
I'll be happy to share with you our recent insights concerning a connectomic hypothesis about the hominization of the brain. So let's start with it. What motivated this approach? What motivated is the following. There's an apparent paradox concerning the enhancement of our largely unique human abilities, like theory of mind and language. And this expansion of the human brain and our cognitive repertoire took place against a background of apparently few changes in the number of and kind of genes. Please change the slide. So as we see here, there are brain protein coding genes involved in several neural substructures and synaptic organizations, and are found to be more conserved. We see that in the bottom panel to the left. They're more conserved than genes related to other parts of the body, and testes actually stick out as more human-specific compared to other primates. So there's like this general uniformity pops up from examinations like that of the coding genome. And this illustrates a so-called astonishing evolutionary parsimony of genetic information during the primate lineage. So against this background, and relevant to this workshop, we propose a connectomic hypothesis of the hominization of the brain as a parsimonious explanation of certain key organizational elements that led to the brain of ours to be the way it is and have the capacities that it has. So next slide, please. A key phenomenon that will occupy ourselves in this talk and constitutes a key factor explaining a variety of connectional alterations in the human brain with respect to other non-human primates is the size and what effect this enhancement of the human brain size it has with respect to network architecture. Let's unpack some basic aspects. The key phenomenon here to pay attention to is that brain size increase causes a shrinkage of the horizon of connection and probabilities. So let's unpack it a bit with this toy example that we see in the right. This toy example will make more sense when we consider axonal growth as an isotropic random process. So in this example, the probabilities of the gray neuron to reach and form a connection with a proximal neuron like the purple neuron, these probabilities are higher when compared to the probabilities of reaching and establishing connections with a more spatially distant neuron like the cyan neuron. So that's mere fact of probabilities. With increased distance, we have to navigate more material and avoid more connections and use more information to bias the action to the right direction. So it's a pure relation of space and probabilities. So increased size then overall decreases the probabilities of connectivity, thus constituting a factor for the sparsification of the network of our brains. So in other words, to recap, we have a shrinkage of the horizon of connection probabilities related to increased brain size of the human brain that in turn leads to the overall sparsification of the brain network in humans. And in the next slides, we'll see some more concrete network topology features that this sparsification leads to and functional consequences thereof. Next slide, please. Here we will occupy ourselves with sparsification and modularity. Increased sparsification has been demonstrated to lead to increased modularity, that this more tightly interconnected set of neurons, so-called modules, are formed. And in order to test now the functional consequences of this enhanced modularity, we can focus in this example that is an amalgamation of network science and ecostate networks to showcase concretely the functional ramifications of modularity. So what we see here is on the left, we have a network configuration with low modularity, and to the right, a network configuration with high modularity. And if we now, along the spectrum, we plug in this network topology in an ecostate network that we see on the top, and then examine the capacity of this network to store a number of sequences in memory and how lengthy this duration of memory will be. As we see in the figure to the right, with enhanced modularity, with high modularity, we observe a higher number of sequences that can be stored in memory and an enhanced duration of memory. So in other words, this in silico exercise highlights the consequence of having a more modular configuration. So the take-home message here is that increased brain size leads to sparsification, and a consequence of sparsification of the network is enhanced modularity that in turn enhances sustained activity and working memory. Next slide, please. Here we will occupy ourselves with the consequence of enlarged brain in humans compared to other species, sparsification, abstraction capacity, and also a couple of words about increased plasticity of the network one. First, we focus to the left, panel A and B, and we will go through some basic insights that stem from classic work in artificial neural networks. As we see here on the top, we have a simple feed-forward network that has as a task to decode the location of an artificial synthetic agent that explores space. So the goal is from raw pixels fed from a camera to decode the location in a 2D arena where this agent explores. So that's its world. So as we see in the panel where the little robot is, the synthetic agent, so panel A to the right, with increased hierarchical level, we have a decrease in the reconstruction error of the location of the agent. So that means the agent can abstract from the immediate information receiving from the sensorium and reads at a higher construct, in that case, space, location in a space. And we see that increased level actually is accompanied with decreased error. So it learns better this abstract concept, location in that case. So let's now bring this basic concept from artificial neural networks in our current exposition, or in the current topic. We see here in panel B to the left that the increased size and constant spatial drift of the sensory areas and the constant enlargement of association areas might have led to such a configuration that there is a decrease of the crosstalk in terms of connectivity between sensory modalities, as it is the case in the mouse, and an enhancement of the steps, the hierarchical levels from the sensorium to the so-called network core, which corresponds to limbic and association areas. So we have actually here a manifestation at the evolutionary level and with some insights from artificial neural networks of some classic ideas, for instance, from Mesulam, as exposed in his classic From Sensation to Cognition. So to recap, increased hierarchical depth purely as a consequence from increased brain size and expansion of association areas may bestow the human brain with increased abstraction capacity from the sensorium. So let's go now to the right. We have a manifestation here of the phenomena of the displacement of the network core evolution. What this means is the following. Let's focus on the top diagram. We see here that if we separate brain areas between core and periphery areas and assess how they are segregated in terms of microstructural properties that are directly linked to plasticity, such as the level of myelination, we see that a transition from mice to human also involves an increased microstructural segregation of the core and periphery areas of the network of the brain. So in other words, in humans, we have an enhanced segregation of the core and periphery areas of the network, with the network core encompassing to a larger extent the more plastic areas of the brain compared to what is the case to non-human animals. So in other words, we have increased network depth and increased plasticity of the network core, wherein the more abstract levels are achieved. So let's now, please change the slide. So let's now proceed to some changes that have to do not with brain size expansion per se, but with microstructural properties. Here what we have is the so-called phenomenon of external pyramidization, a bit of a cryptic name, but let's break it down. So what we see here on the top panel, panel A to the left, we see three classes of areas. From to the left, we have areas that elicit the majority of their cortical connections predominantly from deep layers. Areas to the middle, in the middle, highlighted with gray, that have a more balanced origin of connections from upper and lower compartments. And to the right, denoted with pinkish colors, we have areas that predominantly elicit their connections from upper layers. So we have in the two extremes, two classes of areas, externopyramidal on the right and internopyramidal to the left. And externopyramidal areas primarily have connections from upper layer compartments, and internopyramidal on the other end of the spectrum, they have areas predominantly from deep compartments. And of course, in this spectrum, everything in between is also possible. So now, due to reasons that for the interest of time, I will just compress them and refer them to you for more information to this publication of ours in TINS, this reference that I have here, 2018, where we make the case about the shift in humans. So based on this hypothesis and converging evidence, we have in humans, as we see in the bottom panel here to the left, we have in humans more areas that have this externopyramidal character. So that means in humans relative to non-human animals, the propensity of connections, the cortical connections, is to emanate from upper compartments, from layer 3 specifically compartments. So now why this is important? Let's say that, okay, this is indeed the case. There are some converging evidence that dictate that this is the case, but someone could say, so why is this important? What is the functional consequence thereof? The answer to that is observations at the microstructural level that come from developmental studies. And now I would like you to focus to the right panel. There we have some events that pertain, for instance, in panel A to the right, to the soma surface of layer 3 neurons and soma surface of layer 5 neurons. So now if we see these curves and how they coincide with the critical period between 2 and 5 years in humans, we see actually that the stabilization of layer 5 neurons in terms of soma size happens much earlier, contrary to the stabilization of the soma surface that takes place around this critical 2 to 5 year period. On top of it, we have at panel B developmental evidence that pertain to dendritic growth of layer 3 neurons. And as we see here, we have two rounds, two rounds of the dendritic growth. The first stage, it takes place between 1 and 2 months. Then we have a dormant phase, and then we see again a second round of growth around 2.5 years. So now, if we have in mind these developmental microstructural changes in mind, namely that only layer 3 neurons are selectively, so to speak, undergoing changes around the critical period of 2 and 5 years, and we combine that with the fact that the majority of connections in humans emanate from layer 3 neurons, then we can see that the majority of cortical connections and the corresponding microstructural properties of the neurons that elicit these connections are bound to change around the critical period of 2 and 5 years. And this is important. Maybe it's too small, the graphic, but around this period, if we follow the cognitive developmental literature, we see that aspects that are uniquely human, like theory of mind and language, is really a critical period for such cognitive capacities. So to recap, please change the slide. Very briefly, I hope to have given a glimpse on what we considered as so-called connectomic fundamentals of brain hominization, and why they are potentially important to pay attention to, because they are appear to be uniquely human, B, they parsimoniously arise primarily due to the enlargement of the brain and the entailed sparsification. So we explain how dramatic changes can emerge against the background of evolutionary genomic parsimony. And third, it pertains to cognitive capacities that are presumably linked with these critical periods and connectional architectures. Thank you very much.
Thank you very much, Alex. It was a beautiful work, and
Thank you.
maybe your subdued voice gave it a very nice, soothing undercurrent, because I really enjoyed it a lot.
Yeah, I hope it was not too soothing, but
No, not at all. So in essence, you're saying that the genetic material is more or less present for all these morphological and cellular processes from way down the phylogenetic tree, and all evolution has to do is exert a pressure on growing bigger brains, and everything is sort of gifted for free under the assumption of sparsity. Is that another way of looking at this beautiful work?
yeah, that's the core idea, that many things emerge, so to speak, for free due to this causal links between brain enlargement, sparsification, and topological properties that come with it. I went through modularity and also this enhanced of hierarchical levels and increased levels of abstraction. So that's the idea, to not to have this classic idea that, for instance, we need specific genes to code for specific network topologies, but adopt a more parsimonious and someone could say more realistic standpoint, namely having this causal chain where one event, seemingly very simple, can be sufficient and causal in a causal way to give rise to these important connectional features that seem to pertain to brains at a more enhanced level, not that they don't pertain to other non-human animals.
But interestingly, I mean, they were sort of latent in the smaller brain. These principles that emerge, this principle of differentiation that allows us to have core high-level cortical hierarchies, and the associated histological differentiation. They're sort of latently present, but presumably then not serving the same sort of function that they're preserving under the effect of a larger brain. Or on the other hand, do you think these principles are present even if they're not fully expressed? They're still providing an adaptive advantage to the primates with small brains?
I think your question points out to an important distinction. We point out differences that are not of kind, but of degree. So it's not the case, as we know from comparative connectomics, that other species don't have a modular brain or so. But the hypothesis is that this is a different of degree, like that it is enhanced, or that other species are not, well, the term hierarchy has many meanings, but in the current context, we cannot say based on comparative evidence that other species don't have an hierarchical organization, but this hierarchical organization has acquired more depth in humans due to the reasons and other things potentially that I highlighted. So it could be seen actually as a stretching and modification of a basic blueprint that arrived at a critical point where it was sufficient to give rise to some functional abilities that led to our capacities, which is currently a bit obscure, but that's the idea, because the causal link between what we highlighted and, let's say, cultural aspects, yeah, it needs more time to expose, and maybe Jean-Pierre can say more about it.
Jean-Pierre, would you like to jump in? And I can share the slides again if you'd like.
Thank you very much. And thank you, Alex, for your presentation. And I may say a few aspects. No, I think it's okay. The relationship between the genome and the evolution of the human brain. So the general attempt that we tried to do with Klaus and Alex was to try to establish how this genetic evolution, because we of course have to say that between the Australopithecus and Homo sapiens, there has been a genetic evolution. So few genes have changed because the actual, looking at the actual organization of the genome shows very little change, but nevertheless, there have been some change. And these change had dramatic effects in the past million years, because that's, if you wish, the change from the brain of Homo habilis to Homo sapiens. And there is almost a doubling of the size of the brain, but also quite a very significant change in the overall organization of the brain. And the aim of this paper, together with my partners, was to try to see how only a few genes can have some effect on the evolution of the connectome. So the main issue is that how to relate change in these connectivity features with the evolution of the genome. And so we have in the paper presented quite a number of possibilities, but what we wanted to say is that most of these genetic change are regulatory genes. So that's no longer the view, one structural gene, one phenotype. These are mostly, we think, regulatory change, regulatory mutation or gene duplication. And the notion of connectomic fundamentals that we propose was precisely to see to what extent some elements or some properties of the brain connectome can be selectively, quantitatively changed mostly. These, as I said, these are regulatory genetic effects. So that we save, if I may say, quite a number of genetic determinants, which are common to the overall genomic organization, let's say, of the monkey or the chimp. And here have these few genes affecting the, for instance, the size, the hierarchy, the shift from lower to higher layers. And most of all, I think, perhaps I may add this to what Alex said, which is okay with me, but may emphasize the issue that in humans, the postnatal development of the brain is the highest which is ever seen in the animal range. So this duration of let's say 15 years after birth is of course of extreme importance, and several of these connectonic fundamentals, in addition to that one, because I consider that the extension of the postnatal period is a connectomic fundamental. The overall combination of these different features, together with the extension of the postnatal, and also to the issue that perhaps, which was in the early, quite emphasized in our paper and not too much mentioned here, the notion that there is a selective stabilization of synapses, which is taking place during the overall, this overall postnatal. So there should be an additional element in this slide with this postnatal development. And I may say that this synapse selection is very important because it introduced some variability. Yes, that it is here, taking place here. It introduced variability in the distribution of the connection, even in fully identical twins on the genetic point of view. So this variability, of course, is extremely important, and is taking place within the whole genetic envelope. And that's where why did we select this period, and why we emphasize this interesting second growth spurt around 2 to 3 years, is that precisely the language get organized at this stage. This, if you look at it, it coincides with the organization of full sentences in the newborn. And this is a critical moment, which coincide also with the acquisition of the theory of mind, and which may, in fact, coincide with what Chomsky called merge. So the issue of the synapse selection and synaptic variability introduce the possibility of having different language within the same genetic framework to be imprinted into the brain. And I think this is, of course, an extremely important aspect of the human brain and of the connectomic hypothesis. And if I may say, most often people who are involved in pure connectomic of the human brain most often forget about this variability. And in fact, there is a very significant variability of the connectivity associated with language learning. I was a little bit too long, sorry for that.
No problem. Lots of very interesting depth to this story as well, as you say. This dramatic evolutionary picture, but also all the diversity between individuals living at the same time.
So this is something we emphasize at the end of the paper, which most often is forgotten when you speak with connectomic people. They don't take this into consideration, even though it's a very, very interesting feature of the actually the human brain in particular, because throughout this long postnatal evolution, there is something which is added to the system, is what is called culture. And it has been also emphasized that the humans are submitted to pedagogy. There is a pedagogy which corresponds to the transmission of information from one generation to the other. And of course, it is interesting to realize that we proposed that this late period, which is postnatal, coincide with the impregnation of the human brain with a particular particular culture, and which account for the diversity of language, diversity of belief, and so on and so forth. So this is a very human characteristic feature which does not exist in, of course, in monkeys. And also, I was glad that Alex emphasized also the working memory issue, because one, as a consequence of sparsity and modularity, because this working memory is a good character which differentiates monkeys from humans. And the working memory is, as you know, 1 or 2 items, while it's 7 items in the case of humans. And in fact, it is thanks to this increased capacity of the working memory that one can build sentences. Actually, and here, this is what's happening. The human baby is able to organize a 3-word sentence, which before he cannot, he or she. And this, I think, again, is striking features which contrast with the brain of the monkey, and which we believe is accounted for by this connectomic hypothesis, as it is explained in the original paper in the cerebral cortex.
Can I jump in here for a second, Michael? I want to come off that very important insight that Jean-Pierre just shared with us, and also with the concept of the modularity, and sort of getting back to, I know that you guys haven't been here for the whole conference, but there is sort of an idea of the movement between segregation and integration in terms of brain networks. And yes, if I understood correctly with what you just mentioned, Jean-Pierre, as well as what Alex is talking about, is that by having the sparsity increase for the human brain, you have an increase in modularity. But I wonder if that also comes with the change in the capacity to integrate.
Yes.
Because obviously to form sentences, for example, you need to, like I'm doing now, I think at least I'm doing it well, you have to actually keep track of what you're talking about, which requires integration of both what you're going to say, but what you also said, which is much more difficult, of course, if you have a network that doesn't have the capacity to both segregate information as well as integration. So I'm wondering if the secondary consequence, which I wasn't quite clear on, of having the sparsities, you actually increase the balance of segregation and integration, so you end up with a higher capacity for information integration by virtue of the way the human brain is organized.
Yeah, may I answer to this? I think you raise a very interesting question. And in fact, in our hypothesis, there is a second aspect, which is the hierarchy and the increase of the number, and also the shift from the lower to higher layer, which correspond to a very interesting shift at the cellular level. In fact, it is a shift, yes, this one here, which is in fact the main aspect, the main benefits of this, not only higher order hierarchy and layer shift, according to what Alex has beautifully shown, is of course the global neuronal workspace. Unfortunately, our excellent friend Alex did not mention the name. We did it, of course, in the original paper. And this, in fact, also this core periphery segregation correspond, in fact, to not the diversification of sparsity and modularity and so on, and the development in the higher layers of neuron from the upper layer of the cortex with long-range horizontal axons. And I think we have not only diversification you showed in the previous slide, but also integration through the global neuronal workspace, through long-range connectivity, which link horizontally different areas of the brain. And this is clearly explained by in the paper and by Alex himself. But I understand that he had to be short and did not perhaps wanted to enter into the issue of conscious processing.
Yeah, I left it for the discussions, I'm here, so that, you know, because I had a limited time because I'm sick.
No, I understand that. No, don't you don't have to worry. But I just that's that I think the paper is there for those who are interested. So, but just to say that, because and to answer to the issue of diversification integration, and I want to say that our hypothesis account for the two. The more diversification you have, the more integration through the long-range connectivity you have. This is to respond to Randy.
Perfect.
Are you pleased, Randy, or not?
That's exactly what I was. Yeah, I'm very happy. It's actually, and I read the paper and I loved it, and I'm glad that we actually covered the whole spectrum of the paper. It's a very comprehensive paper, and I think there was a lot of jewels of wisdom that I think are worthwhile considering carefully. And what we just talked about, I think, taps into the notion of consciousness in the global workspace quite well. So it was nice to have that come up in the discussion. Thank you.
Thank you very much.
Hey, I'll just go to the Q&A box here because there are a few questions coming from the attendees. One would be to define a hierarchical level, please. Now, we know hierarchies intuitively, but there is some debate conceptually about how restrictive we should define hierarchies and or how conservative and liberal we can be. As it pertains to this slide, how do you see the definition of a hierarchical level?
Yeah, that's a good point. So it comes with different flavors and different uses in the literature, as you point out. So in the current context, we have to consider hierarchy as synaptic steps. So it's purely like how many synaptic steps neuronal elements have to traverse in order to reach each other. So it's synaptic steps basically here. So it has nothing to do in this Velleman-Van Essen style, although in some ways it is aligned and we can expand in that level.
Okay, thank you. Let me just scroll down. Samuel Rinken, would you like to ask this question? Okay, I'll read it out. Thank you for the talk. I was wondering if you have seen or think there is a proportional increase of neuronal modularity and increase in brain size. Essentially, is the increase in modularity across the animal brain to humans simply proportional to the increase in brain size? So, or are there other sort of topological forces at play here?
That's the underlying assumption. Unfortunately, This has, of course, to be measured directly. And for that, though, we would have to collect data from different species, which actually researchers, that I will point out, have done, to avoid biases of differences in the results based on the modality. And that also, along with brain size, can answer this question. So the people that collect such data is Roger Mas. He collects kind of a primate phylogenetic tree based on neuroimaging data. And also, I forgot the name of the other person from Israel. They have a beautiful database called MUMMY. So it's diffusion imaging of a really, really big palette of mammals. And I think Olaf Sporns works with them. So apologies, I forgot the name, but I've seen a paper of theirs. It's really beautiful. So in principle, these questions can be answered. Yeah, exactly. Thank you, Yanni Fasev. Yeah, sorry. So these questions can be answered with these comparative connectomics datasets that we currently have. Well, we as the community, we have at our disposal. So to make a prediction, I would say that definitely modularity would be correlated with brain size, with some secret sauce there, which we can unpack, but I think there will be a correlation.
Well, of course, there's other examples of mammals with very large brains, dolphins, whales, and elephants that scale in proportion to the body size or above. These just may be examples of brains that haven't been looked at through this lens yet, but although these are intelligent animals, they don't seem to possess the sort of language and culture of humans. And I know that's very anthropocentric, but just to wonder if your thoughts on mammals, other mammals with very large brains.
Absolutely, that's a good point. So it's nice that you have the slide up, because if we look at elephants, for instance, well, they definitely have a bigger brain than humans. But what is interesting, if you look at the distribution of sensory areas and association areas, you will see that despite the fact that they have like this really big brain, the sensory areas have not been drifted apart from each other, interdigitated with association areas, but they lie really close to each other. So for instance, if you look at elephants, the S1 is really close to V1, for instance. So what this means is that, at least with respect to what I highlighted here, we don't have this drifting apart and connectional isolation of sensory areas and their need to communicate only through a prolonged stage, through prolonged hierarchical levels with the core. So that's, I think, one difference that puts aside humans with other species that have larger brains. It's this lack, despite the increased brain size, lack of spatial drifting and consequently connectional isolation of sensory areas, and the lack of communication predominantly of these areas through a network core.
Yeah, very interesting.
For concrete, for concrete maps of highlighting what I just said, you could look at work from Paul Munger, for instance. There are concrete maps of elephants, some African elephants. I don't remember the exact species, but it points out to what I just said.
A few other questions that I'll just read out for the sake of time. Jean-Pierre, do you have a point you wanted to make?
One comment, just to add up to what Alex very nicely mentioned. If you just take the very classical Brodmann scheme of the monkey brain and the human brain, just look at it. It gives you the number of main cortical areas, which has been, of course, since then refined. But when you look at the prefrontal cortex, which is precisely an association area, there is a dramatic increase of the number of cortical territories. that you see in this region. And so there is not only more modularity taking place there, but also a diversification of the cortical areas which do not exist in the monkey. So this is extremely beautiful to look at the level of the prefrontal cortex, and possibly also other association areas. That's it.
Yeah, on this point, we'll come to the questions in a moment, but a thing you said a few moments ago came up in a paper that was recently released about evolution and culture. And a segue to this was a bizarre survey of humans and what animals they thought, men in particular, think that they could beat in a fight, including bears, eagles, and elephants. Now, the bottom line is that we are so dependent on culture and language for survival that we're lost a lot of the basic survival tools. Of course, we'd be exterminated by these beasts within a few seconds. And it's interesting that we really would be terrible to survive without culture and language. So we've these heteromodal and prefrontal areas, you know, given up on the need to be able to go out and sort of survive hand to mouth.
Yeah.
And that may be why we've been able to sort of impoverish compared to elephants the size of sensory motor cortex.
Yeah, what is clear is that as far as the social relationship compared between humans and elephants, there are some social relationship in the elephant, and of course really no language. But it's clear that the expansion of the prefrontal cortical areas and others actually in humans are associated with the social life. We talk in the paper about theory of mind, and language is exactly that. So there has been, as you say, a very strong pressure for a social brain. And I may say that most often the notion that neuroscientists are working with a social brain in the case of human and in the case of mouse of a very poorly social brain, and often goes from mouse to humans, I think it's a dramatic mistake in my view. And this actually connectomic hypothesis give us the space for the brain to be social, because essentially of this postnatal method and the epigenesis, which is taking place through these 15 days or 20 days, 15 years or 20 years of development.
Now,
and
there are some...
The elephant has not that. I think the postnatal development, the environment, the effect of the social environment and cultural environment on the brain of the elephant is not as important as it is in humans, of course, not at all.
So a few other questions, and then we'll have to move on. But this has been a fascinating discussion. One question that I think from Andre Lupi that I'll ask, because we're nearly out of time, but it's really evident in this left-hand side of the slide here, and I think it relates to what Randy was talking about. You can see the emergence of sort of critical bottlenecks in these deeply hierarchical networks, which could be something of a liability. So the question is, what are the mechanisms for which the brain compensates for these core periphery bottlenecks?
Yeah, unfortunately, there are signs that actually we don't cope with them. They have there's a price to pay. So, namely, more propensity and vulnerability to disease, so to pathology. And there is a paper corroborating partially some theory that actually comes up with the idea that the price for increased cognitive capacities and the underlying connectional topology that comes with it is actually the cause for manifestation of psychiatric diseases. And there's a paper that corroborates that from Martijn van der Heuvel, where they show that actually more uniquely human connections are more predominantly depleted in pathology that they examine. I think they compared schizophrenic patients and, yeah, my apologies, I don't remember. But the point is that uniqueness of cognitive connectional features comes with the price of being more vulnerable to pathology. So it's a bit of a manifestation of what Freud said, like culture is the price to pay for pathology. So yeah,
you can see the hubs in that network, and the notion of hubopathies that Ed Bullmore and others have raised. There's so many interesting conversations or discussions, questions coming through. I might just, sorry, Randy, read out one or two more of these, and then we'll segue into your talk. Is that okay?
Yeah, we started a bit late because we had that technical problem, so no worries at all.
Exactly, yeah. So another interesting question here is, well, there's two questions, but they're both related. Synaptic pruning during neurodevelopment with an individual, how important is that to contributing to these sparse and modular networks? And then I guess at the other end of the lifespan, during aging, in which there can be loss of hubs and other things. Have you viewed the human lifespan through this lens?
I haven't done studies that are developmental, but there's literature from Damien Fair, for instance, and his colleagues, that the early developmental connectomic studies, that they have shown that indeed with age we have a predominant shift to more modular structures and loss of certain connections. So it might be related, I would say.
And synaptic pruning during neurodevelopment?
Synaptic pruning for sure happens. Now, how exactly it contributes to modularity depends on what connections this pruning involves in the topology. So it could be pruning that my guess would be that, of course, it would enhance modularity, because first connections that will go with synaptic pruning are primarily long-range ones. Not all of them, because some of them are actually strengthened, but there is a tremendous amount of elimination of long-range connections during development.
Just one word about synapse selection or elimination or pruning, whatever you like. I think it started very early on, for instance, at the neuromuscular junction. And there is clearly at some stage of development, this was shown by Redford and by ourselves in great detail, that there are 5 times more connection than at some critical stage than in the adult. We also showed that in the case of pyramidal of Purkinje neurons in the cerebellum, and there are 3 to 5 climbing fibers at some critical stage of development, which are taking place there. I think there are many observations done by a variety of scientists who clearly show that you have throughout the whole development, this synapse selection is taking place from the beginning to the end. Of course, the overall loss of synapses can be very high, because if you look, for instance, I have not the slide here with me, but this is well documented, that as a function of the age of the child, at the time of before puberty, between 3 to 12, there could be the global envelope of synapses of the whole brain is decreasing by up to 30% in the development of the human brain. This is an evaluation, it's an estimation. So the actual loss is very high. And when I emphasize the aspect of the variability of the connectomic of the human brain because of synapse selection, I think it's starting from the very beginning until the end. So this kind of variability is one of the main characteristics of, if I may say, of the mammalian and most of all of the human brain.
On this beautiful note, I bring this first talk to a close. So thank you very much.
Well done.
Here. That was just lovely talk.